today we have with us Dr. Babita Jajodia from IIIT Gauhati, who will be delivering a talk on the design of Transceiver Design for IEEE 802.15.6 Wireless Body Area Network System. Dr. Babita Jajodia is an assistant professor in the Department of Electronics and Communication Engineering at the Indian Institute of Information Technology, Gauhati, working from July 2019. Prior to that, she received her PhD in VLSI design from Indian Institute of Technology, Gauhati. Following that, she worked at the Gauhati University Institute of Science and Technology as a guest faculty. Her research work includes VLSI design for digital analog mixed signal systems and quantum computing. I would like to hand over this session to Madam Babita Jajodia so that she can deliver her talk. Thank you.
Yeah, thank you, Mr. Kalita, for handing over the presentation and for permitting me to take over this. And I'm privileged to be a part of the ATAL FDP organized by Gauhati University. Okay, so let me share my screen. Can anyone just confirm whether it's visible or not? Yeah, are the slides visible?
Yes, madam.
Okay, you are able to see the slides, right?
Okay.
Yes. Okay. Okay, so due to some unavoidable circumstances, I'm not able to turn on the video. Yeah, I apologize for that at the very start. But before I start the presentation, I would like to mention all of you. I'm also the beginner in the VLSI, right? So I will just try to make you all to come in the direction of VLSI, and as a practical also, it's known to us, right? In a 1.5 hour, it's not able to cover up entire topic, right? But I will give you a glance and how anyone wants to do research on this domain can definitely work on that. Yeah, and I will be pleased enough if anyone asks me questions at the end. We will take the question answer round at the very end of the session. Yeah. Okay, so with this, I start. Just a minute. I think there is just a minute. Yeah, sorry for the delay. Yes. Is the screen visible now?
Yes, ma'am.
Yes. Okay. Thanks a lot. Yeah. So with this, I start the presentation. Yeah. So welcome everyone to the FDP program. It's in the third day of the session, right? And already you have attended one session. So I will try my best not to bore you. Yeah, and please, if one of the participants starts working on the transceiver design, might not be for wireless body area network or might be for another applications related to the VLSI, I think my talk on the ATAL FDP is a successful. Yeah. So with this, I would like to mention the title of the presentation which I will be giving is the Transceiver Design for IEEE 802.15.6 Wireless Body Area Network. I myself, Dr. Babita Jajodia, am working as an assistant professor at IIIT Gauhati. So before we start the presentation, yeah, so I would like to tell you from the title itself what we are going to learn or what we are going to know about the research in this talk. Yeah, so first of all, it's a transceiver design, right? So whenever we say transceiver design, it basically the transceiver words itself indicates it's a combination of transmitter and receiver, right? So basically we will be discussing about the transmitter and the receiver design, right? Then IEEE 802.15.6. So this itself indicates like it's an IEEE standard, right? Which is specific for the wireless body area network. Okay. So next comes, we mentioned like wireless body area network system. So when we say system, we will be discussing the transceiver design, but keeping into perspective the system perspective as well, right? We won't be working on only single blocks, we will be working on blocks, but we will take into consideration the entire system level as well. Okay. So wireless body area network, the name itself indicates like the wireless means the transmission will be done wirelessly, and when it's a body area network, it means we are covering a network in the area of the body, right? So it can be on body, then it can be internal, like you can put in capsule implantable as well, or on body as well. Okay. So to summarize it up, so basically in this talk we will be discussing about the design of transmitter and the receiver for particular wireless body area network and pertaining to the particular standard, which is 802.15.6. The last number itself indicates it's a wireless body area network. If it's 15.4, it's known to us that comes under the wireless personal area network. Okay. Okay, so as like a brief introduction about myself, like as Mr. Kalita has already mentioned, I work at the Department of ECE at IIIT Gauhati, and prior to that, I worked on the Gauhati University as well. And before that, I pursued my PhD in VLSI design under Professor Anil Mahanta and Professor Sheikh Rafi Ahmed in the domain of VLSI. Yeah, and very recently from the last year, I have started working in the domain of the quantum computing as well. And I welcome everyone if anyone is interested for the research collaborations, as well as the student participants or the postgraduates or the research scholars. If anyone wants to do internship, he or she are welcomed in my team. And before that, you have to send me a mail with an internship and how much duration and what is your interest. Yeah, if anyone wants to explore more on which area I work it up, he or she can visit our institute website as well. Okay, so the outline of the presentation, what we will be discussing. First, we will discuss a brief introduction about, as I mentioned, like about the transceiver wireless design of wireless body area network. We will discuss why we want to design the transceiver, right? What is the history behind that, and why all of a sudden, after the standard has been finalized, why we have started working on that, right? Then we will be discussing more on a brief description of the transceiver design. At the transceiver design, as I mentioned, it covers the transmitter as well as the receiver. So we will be discussing about the transmitter and the receiver design for the particular standard. But here, if you note it closely, we will be discussing it with respect to the IRUWB. And the full form of IRUWB is Impulse Radio Ultra Wideband. So the standard 802.15.6 has given up various like frequency domains. So like narrowband, IRUW band, as well as the frequency modulation part also, right? But we will be discussing like on the IRUWB because it has an advantage that it makes an optimize as well as a low power consumption due to the like maximum bandwidth. So generally IRUWB covers up in the range of 3.1 to 10.6 gigahertz. Okay. So this itself signifies that for this we need the pulse to be sent in the transmission of the minimum width. This itself increases the bandwidth. Okay. So then the third we will discuss about the DAC switching technique, which is one of the block which has been incorporated in the receiver. Yeah, so we will discuss a little bit about like when we say energy detection, right? So it's basically the signal will be received at the receiver end, right? Then it depends on how you are demodulating it, right? There are different types of modulation, or you can say different type of receivers like coherent receiver, non-coherent receivers, right? Coherent receiver gives optimal BR versus SNR, right? But it comes at the cost of designing a template generator in the receiver as well, right? But non-coherent is basically, it does not require an template to be generated at the receiver end, right? So we will discuss this why we took into this consideration. Okay, then we will discuss like once energy detection has been done, so that energy whatever has been collected, as we will be forwarding it to the baseband part to process, right? So we have to convert this analog because this will be an analog value, right? So we need that in the digital to make the baseband part to be taken care, so we need a ADC, right? So basically, since energy part, once you take it up, it's only a positive value, right? So based on, since it's only a positive voltage, right? So we will be targeting to use a single-handed SARDSE. Then what we will be discussing a little bit, if time permits, right? How to design the PWLA waveform generator. Yeah, so this we will discuss one by one. But basically, we will be focusing on the first two points, okay? And then we will be discussing about the conclusions and the scope for future work as well, if anyone is interested to work on that. Okay, and the full form of PWLA is piecewise linear approximation. Because pulse will be required when you are transmitting, right? It can be for generally in the IRUWB or UWB, we use the Gaussian pulse and etc. Right? So how to design it? When we say Gaussian pulse, right? We use a function generator and etc. We transmit, but in the real time, it's very hard to generate in the hardware, right? In the VLSI hardware perspective. So we have to take few approximations. So we will be discussing about that. Okay. So with this, we start with the introduction. Yeah. So any doubts till this point? I think it's clear, right? What we are going to cover it up. Okay. Okay, so we start with the introduction. Yeah, so when I say introduction, so basically we will discuss about what do we mean by body area networks. So body area networks, again, it can be two types. It can be wired or it can be non-wired as well, right? So this is the generalized one, and based on the standard only, it has come to be a W band. Okay. And previously, before the standard was not given, right? People still used to make the body area networks, but they start using the convention of the W pans. Okay, but there were few points, like for example, SAR, so specific absorption rate for the W pans, that might be harmful for the human body, right? So based on that, the IEEE 802.15.6 has tried to take all that points into the consideration so that the radiation pattern and etc. does not harm the human body. Okay, then we will discuss few things about like what are the research works which have going on in the PANs, right? And what are the wireless solution? Can we use Bluetooth, Zigbee, and etc. Right now, IoT is a boom, right? So IoT is also, you can say, when you use for the healthcare application, it's somewhere sort of you are designing it for a body area network as well. Okay, and then we will discuss a little bit about in details about the standard as well. And for your information, like the standard was finalized in the year 2012. Okay, then we will discuss a brief literature review on like the transceivers for the bands which are still present. Okay, so when we say introduction, right? So as I mentioned, so when we say body area network, why we need it? The first question that comes to our mind, why body area networks, right? So basically the concept of this has come for the active wellness management, right? And what will the advantage of this? It will help for the early diagnosis before it's too late, as well as it will help for the detection of elements and follow-up actions. For example, someone has an heart attack, right? And like if we are not able to make the patient reach the hospital immediately, he or she might have a casualty, right? So if someone says like, okay, I am having a chest pain or etc., so a little bit minor treatment can also taken care until he or she reaches the hospital. Okay, and then when warranted, right, when you come to know you have something, so you can take the emergency action. So might be doctor might have suggested you take this medicine so that within that 1 hour or 2 hours, it will be okay, and like you can reach the hospital. And as well as improving the quality of service. Yeah, so that's the most important thing whenever we say like we want to make the body area network to be feasible to be used, or like might be for any other networks as well, the quality of service is the most important which is required, right? So now when we say body area network, so what are the basically requirements, right? So it can't be like multiple wires and everything you can place on your body and you can move 24 hours, right? It's not practically feasible, right? So when we say the application of the body area network, it basically requires low power. Basically, it should be low power, right? So that's where the active area of research is, and everyone is trying to design the body area network system in such a way it is a low power, yeah, and it should be a minimum size, right? And when sensor nodes. So when we say body area network, right? So there can be a master node, right? And there can be one sensor for the ECG, one for the EEG, and etc., right? So all the sensors will be placed on the human body, for example. So they should be minimum sized, right? So that it can communicate with the master node as well, and it's easy handleable for the human being as well, right? So now the sensors, whenever we say this, can be placed on the body, or it can be placed around the body, or it can be implanted as well. If you have gone through the literature, or like in the prior, you can see like endoscopy these days are also done by taking a capsule. Okay, so it's like an implantable, as well as you can see like for the cardio and etc., right? The pacemakers are implantable. So when we say pacemakers are implanted, so it should be lasting for a longer time, right? So battery should be lasting around 8 to 10 years, right? So the battery power, or it will be related to what is the, just a minute, yeah. So it will basically depend on how the energy will be distributed. So it should be low power, okay, and it should be having a constant health monitoring. It should not be like it's working for some time, it's not working for another time, right? So the basic requirement whenever you say body area networks to be in practice, right? It should be low power. It should be minimum size sensor nodes so that it can be placed on, around, or it can be implanted in the human body, and it should have a constant health monitoring, and it can also take a feedback from the doctor and can advise the patient what to do next until he or she is able to reach the doctor. Okay, so now comes like why I mentioned like transceiver design, right? So in a typical body area net sensor area node, right? So you can see like the maximum 50% of the power consumption is being taken by a transceiver. So you can say like if you are able to make this 50% to might be 45% also, right? So that's somewhere like you are saving the power, right? So everyone puts small contribution as well, that itself will lead to make an efficient transceiver which can be applied for the health monitoring systems as well. Okay, so basically the target of what I want to mention in this presentation is basically we will be understanding a few points from the VLSI perspective, like how we can implement the transceiver architecture for the particular point low power. Okay, and that can be feasible for the band systems. Yeah, anyone wants to say something?
Madam, the slides are not being changed. The first slide is only visible, madam.
No, it is okay, I think.
I was explaining from this slide only, sir.
Oh,
It is okay, I think.
Yeah, yeah. Okay, so are you able to see now the research work on band slides? Mr. Subho Rao. Yeah.
no, it is not visible, madam. First slide is only visible, presented by your name, and that slide is only visible, madam.
I think, can you just rejoin the meeting? I think there is some network issue at your end, I seems. Yeah, Mr. Kolita, are you able to see the slide?
It is changing at our
Yeah.
end.
I think might be network issue at that end. Okay. Okay, so let's continue this, right? So when we say body area network, right? So when we do any research, we should know what's the history of it, right? And why we are doing it, right? Even if we are working on any research area, we should know why we are doing it and whether it will be required for the human beings from the perspective of the band, right? So when we say bands, right, it was nothing like it started from 2012 when the IEEE standard was finalized. The first research work was already carried out in the radiology research lab, the University of California by Mackey, right? So you can see it started in the year 1959, right? And what he tried to do, he tried to develop radio telemetry from within the body. Okay. Then after that, Zimmerman in the year 1996, he trying to demonstrate how the electronics device, if they place on the human body, they can exchange the information. Basically, when we say body area network, we want the facility to exchange the information, right? So EEG signal should be transmitted to the master node, then the master node can forward it to the doctors, right? So these are various techniques, like he tried to do it using radio telemetry, then this was done through the electrostatic coupling and etc., right? So then like the PANs, as I mentioned, right, the personal area network was also being used, like representing the communication on, in and near the human body, right? So you can say indirectly the BAN is a special case of PAN, right? So where it covers up only on the body, in the body, and the near the body, or as well as the implantable. So this was coined by the Nine in 2001 in the Finland, right? Then Professor Yang, he finally formalized, right? He finally said no need the work of PAN and etc. Right? So let's coin the term and call it body sensor network in his book, right? And this has also been referred as a BAN. So BAN can also be called as BSN as well. So the full form of that is body sensor network, right? So this is the history. It's nothing like from 2012 it started. It might be different communication techniques were used, but it started from 1959. Okay, so this is a brief history how it started working on up. Yeah, so now as I mentioned, right, so the information should be transmitted from sensors to the master nodes or to the doctors, right? So basically when we say to send the information, right, phone also, right, when we are sending the information, either we are sending using the Wi-Fi or using the Bluetooth also, if the person is near my range and etc. Right? Initially, when net were not available in our phone, we used to transfer files and etc. through our phone only using Bluetooth, right? So there are various, whenever we say transmission and receiving, right, generally there should be some radio frequency technologies which will be helpful to do that, right? So if you go through this figure closely, you can see like there are various radio frequency technologies which can be used for the bands as well, right? So for example, if you see this, so these are basically 6 different types of frequency bands which can be feasible. So basically, as I mentioned, like we will be discussing for the IR-UWB, so that is been from 3.1 gigahertz to 10.6 gigahertz. Please note it in the x-axis I have put the megahertz, so that's why it's 3100 and 10,600. Okay. But even if I am presenting it for IR-UWB, that doesn't mean that we can't use the others as well, right? So these are the possible bands, but generally these days everyone are trying to avoid the ISM band because this is already overcrowded, right? So this is the lower ISM band, this is the higher ISM band, and this is the M band. This is also a medical body area network, which is only specific use for the medical applications, okay? So WMTS, this is also a wireless medical telemetry system. So the bandwidth is been mentioned up here. And MICS, this is the very well-known and famous bandwidth, right? Medical implant communication services. So generally, it's like the implantable devices are suggested to be used here because it's a low frequency, so it won't be harmful for the human body as well. And the human HBC. So here comes a very interesting thing regarding the human body communication, right? So it's like HBC. What can happen here? It does not use directly the frequency. Here it's like it's visible, and generally HBC are used for non-medical applications, like for example, audio transfer, music transfer, and etc. as well. Okay. So you can see like it's also called as a human body communication. So I'm touching another person and I want to transmit the like information. So it's like my body has been used as a channel, right? So it's a body channel communication, or we can say intra-body communication. Okay. So whatever the slides, frequency bands I have mentioned, this is a standard protocol and it has been given in the paper, a survey on wireless body area network published in 2014. Okay, now comes the important thing, right? So I was mentioning IEEE 802.15.6 standard, right? So what does it indicates, right? So what are the things covered it up? So whenever if you have seen through any standard, generally it gives the description of the MAC layer and the physical layer. So please note it down here, like whenever we say standard, right, they just give the specification. They say, for example, your power should be this, your area should not area, your transmission should be this, and etc. But the implementation of that is user defined, right? So you can see here, like as I mentioned, IEEE 802.15.6, this was a standard which was coined in the year 2012, right? And it was applicable for the deployable for the BAN system. So we can make a product as well out of this, right? And this is the only formally defined short range, highly reliable wireless communication. Please note it down. The standard is wireless. That's why we can also say it W-band. It does not mean that BAN is only wireless, right? It can be wired also, but the standard specifies basically for the W-band. And as we have already discussed, what are the frequency bands related to that? Okay, so basically any standard defines the MAC and the physical layer, right? The other layers which covers up under the OSI models, that does not come in the scope of this presentation. So when we say MAC layers, right, what does it define it? It tells us about the control access to the channel of all the hubs and the nodes, right? So the master node can also be called as an hub, right? So it tells us how the control should be done, and it should be a single, flexible and sophisticated MAC protocol. Just generally the MAC layer basically designed by the communication engineers as well as from the network engineers, yeah. But when we say transceiver design, the main focus of ours is basically in the physical layer. Yeah, it's also called as the PHY layer as well, right? So here what happens, this physical layer is basically also, you can say, an interface, how to transmit the data from the MAC layer, but it should be under a particular protocol. That's what, right? And the standard has defined 3 physical layers. One is the HBC physical layer, right? So which covers up in this frequency band marked by the red. Right. The second is the narrowband physical layer. So narrowband basically covers it up, WMTS, ISM, M-band and the ISM. This entire is been covered up here. Okay, as well as the MIPS as well. So you can see like one part is this, one part is this, and the third part is this. Okay, so it defines HBC physical layer, narrowband, as well as the UWB PHY. Right. Okay, so and this is the standard. If anyone is interested, he or she can go to the IEEE Explore and can download the standard as well. Okay, it's a 271 pages manual. Okay, so now comes, like, as I have mentioned about the frequency and what is the standard in a brief way. Now comes, like, as we mentioned, we will be discussing about the transceiver designs taking UWB frequency band, right? So when I say UWB frequency band, I will be covering up this green part, right? So now UWB, those who are from the communication, they know UWB can be higher UWB as well as, or it can be multi-band as well, right? And what is the minimum criteria that's required to define a band to be UWB? The bandwidth should be at least minimum 500 megahertz, right? So as I mentioned, for the wireless body area network as well, for the band, the use of the UWB in the bands was not that it started in 2012 only. It started long back in the year 2003 only, right? So you can see the references. So how people started, or how the researchers started to find it out, can we use UWB for bands, right? So the starting point for the use of UWB in the bands were done by Zasovi or something. Yeah, it's like this in the reference number 13. So how did he start it? It's like this, he started investigating of the UWB channel from 3 gigahertz to 6 gigahertz for a band, right? And he started to do it in anechoic channel, right, as well as in the office room, right? Then he found it are the positive results. Then he started, okay, like we can also use the UWB, but he is the first person to start using the UWB in bands. Then the second use was done in the literature number 14, right, where the team has started to use the UWB for endoscopy, right? So that's very complicated, but they started using the UWB for endoscopy, and that was possible. And the reports of that is given in reference number 14, right, where they started doing capsule endoscopy of the, and the project is like UT-COMS, right? The full form is Communication System for Nanoscale USLI, right? And they started designing it for the endoscope using UWB. So it was also a successful event, right? So based on this, what we can say, yeah, we can use the UWB for the transceivers, right? And it can be a very good option for the on-body, off-body, as well as the implantable as well, right? Because implantable was already tried in the experiment of the endoscope. Right, and what will be the advantage of UWB transceiver? It will be low complexity, right? Because we need not to do it the modulation, right? We need not to multiply it with the carrier frequency. As I hope everyone knows, right? If UWB we transmit a small pulse, it can directly go to the higher frequency, right? But in the narrow band, if you take a Gaussian pulse, you have to multiply it with the carrier frequency of that particular band where you want to shift it, right? So indirectly you are reducing the complexity, as well as it will be the low power consumption, and there will be low transmission power. So the minimum transmission power, I think it's around minus 41.3 dBm per megahertz, right? So you can calculate it based on the bandwidth which you use. and the minimum bandwidth should be 500 megahertz. So I think it's around minus 14.3, and it won't be more than 36 microwatt for the transmission. Okay, that's very much less compared to the narrowband. Narrowband generally requires in the range of milliwatt. Okay. Okay, then a brief literature on the implants, right? So Gao, he proposed wireless telemetry system, right? So now this, if you look closely, we are trying to put it in the place of the transceiver. So when I say transceiver, transmitter and the receiver, both we will be discussing, yeah? So Gao, he proposed a system, right? Where he tried to employ the on-off LC VCO based transmitter, right? And in the receiver type, he used a non-coherent, right? So when he used non-coherent, there was no requirement of making a template at the receiver, as well as it was taking the minimum power to design the receiver, as well as energy detection. For example, if your receive signal is R of t, right? Energy detection, what it will be doing? So it will square the receive signal and it will integrate it, for example, from the particular band which you are taking, right? So then Anze, he also performed the evaluation using MAD PPM. The full form of PPM is pulse position modulation. That's somewhat similar to OK also, you can say, but for only 2 array, right? So he also used that as well. And please remember this, as well as please note it down. PPM is one of the most important modulation scheme defined by the IEEE 802.15.6 standard, right? So here what he did, he designed the transmitter, which was based on the PPM scheme, but he tried to put the receiver using correlation detector as well, and the FPGA implemented ED receiver, right? ED is energy detection receiver. So he tried to make it, like you can say, a hybrid model, both having the coherent and the non-coherent receiver. Okay, so based on the literature and the various surveys, it was claimed that the ED receiver is preferred over the correlation-based receiver, because ED has an advantage, like it does not need the generation of the carrier signals, right? As well as the template is not required to be generated in the energy detection receiver. Okay, so whatever the implant this was given, everyone has tried based on the capsule endoscopy only. Okay, and all this were done in the year 2011 2014 as only, yeah. Then now, as we mentioned from the prior slide, right, so the ED is very much efficient compared to the correlation based receiver, right? So based on that, there were various IR-UWB receivers. As I have mentioned, the advantage of IR-UWB compared to the multi-band UWB receivers and transmitters, right? So you can see there are various literature reported on the IR-UWB transceivers using ED principle, that means energy detection principles in the receivers has been employed, right? So you can see all these references 18 and 19, they have used 15.4a. So as this is a wireless PAN network, right? This was done before the standard was finalized in the year of 2007. Okay, then Kyong and Yus, they did this again, designing the IR-UWB transceiver in the IEEE 15.6 2008 standard. So this can be a question from your side, like ma'am, you are mentioning 2012, but why 2008, right? So 2008, what happened before it was standardized and finalized in the 2012, right? A draft was prepared, right? So that the people can start it up working on that, whether it's feasible or not, right? So he tried to work on that based on the various experiments in the next 4 years from 2008 to 11, right? They finally finalized, yeah, this can be used, right? So this was based on the demo or the draft, which can be, it's like many changes might have taken place in the draft from 15.6 2008 to 2012. So please look at, that's why I mentioned the year as well. Okay, then you can see, like based on various researchers on this, there was another second draft prepared in 2010, right? So the team has also tried to design IR-UWB using the draft prepared for 15.6 in 2010. Okay. Okay. So then similarly to this, yeah, there are many other literatures as well, like energy detection principle was done, right, to design the IR-UWB, and Gao was a person who tried to design the digital baseband as well, right? As I have mentioned, like after the receiver, suppose this is a transmitter, right? So you receive the signal at here, then you use the energy detection modulation, so you get the energy, right? So now it should go to the baseband again to demodulate it and tell us, yeah, it's a 1-0 or what, so that it can be forwarded to the MAC. Similarly here, there was a MAC which was transmitting the bits, right? So it went to the baseband part and then it went to the transmitter to convert the bits into the pulse, and then it transmitted. And this is like, you can say, transmitter part, and this is the receiver part. Okay. Then the most important thing, right? So this based on the, now we will see few literatures based on the 15.6 2012 compliant transceiver. So this is what after the standard was finalized. So few literature based on the digital baseband, how did it work it out, right? So you can see Munchie and Bontoc, they have tried to present the digital baseband architectures as well after the standardized. So you can see they are published in 2017 after the literature was found. So here comes the summary of what we discussed, right? So basically, as we mentioned, right, standard was defined in 2012, right? But prior to that also people were using and trying to design the bands. Some might have been using the 15.6 draft manual in 2008 and 2010, but other than that people were still designing bands for using the W band specifications. Okay. And when we say transceiver design, so it has a transmitter and the receiver. So when we say transmitter, then also it has two blocks, right? One is the baseband, another is like pulse generator and how to transmit, right? And in the receiver, also there will be two blocks, right? One will be like after receiving, how to decode the bits. So it can be coherent or it can be energy detection or anything, yeah. And similarly, after the energy detection or coherent, it should have the digital baseband as well to convert it to 1 and 0, as well as like doing the decoding if any encoding is done in the transmitter. Okay. So that's where how the thing was working, and then everyone is trying to make it low power so that it can be feasible for the IoT based device as well, and it can be placed on the human body without harassing, or you can say without putting the person in discomfort, to use the sensors on the whole body for the continuous monitoring systems. Okay. So the most important thing, yeah, so this was one of the very good project which was done by Ovry, right? And the project name was called Ruby LB, right? So this was a system where he has tried to design a hybrid transmitter, right? And it was presented on 15.6 2012 compliant. So when I said 15.6 compliant, that means like it has followed all the specifications mentioned up there, right? So what was his part here, as we have mentioned? So as I mentioned, it should have a receiver and transceiver as well as a baseband, right? So what he did, so that it's feasible for a coherent and non-coherent, he has done a hybrid combination. So it can also be called a smart combination, where he has done a coherent quadrature receiver as well as the non-coherent energy detection receiver. As we have already discussed, energy detection is a non-coherent because it does not require the template to be generated at the receiver. Then this project, or the chip which they have finally prepared for the transceiver, this also had a digital baseband architecture for these dual networks. Okay. Then the synchronization is the most important. This is a very active area of the research, right? So synchronization techniques are very much important, else like synchronize, if it's not, then you will be missing the value, or you will have getting the bit error more higher compared to connect. So this project has also worked on the synchronization techniques as well as the hardware implementation. So you can see all this literature from 30 to 35 has been covered up under the Ruby LB, where they have tried to design this transceiver based on this standard. Yeah. So after this only, when in the reality we could see some chip, there were more active participation of trying to design and working on the wireless body network. Okay, so as we mentioned, yeah, 15.4, 15.6, right? So there were few research as well which were trying to make a single transceiver which is compatible for both the standards. Okay, so Wang was one of the person who tried to design a transceiver for the higher frequency 7 to 9.8, that is under the UWB, where he has tried to employ the duty cycle receiver, right? And where the digital baseband, right, which was developed on the FPG. Okay, as well as another author, Dehans, he also tried to make compliant to both 15.4 and 16 an energy based receiver as well. Okay, and the particular higher frequency 7.2 to 8.5 gigahertz, right? So as I mentioned, right, so the frequency minimum should be 500 megahertz and maximum can be 10.6 minus 3.1, right? So he has used like 8.5 minus 7.2, 1.3 gigahertz. Okay, so based on whatever existing literature and etc., right, so we can say like there are still loopholes, or we can say where and why we can do the research on this, right? So still there is requirement, or you can say still there it's an active research area, how to design 15.6 IIRUWB transceiver, as well as not for IIRUWB, you can design for narrowband or you can design it for HPC as well, right? As we mentioned, like 50% power consumption has been done in the transmitter and the receiver, right? But still there are chances of improvement in that, right? So in this work, or we can say in this presentation, we will discuss like how the individual blocks of the transmitter and receiver can be improved to reduce the power, right? So if someone can says, yeah, transmitter only one block, right? So if you see like there are 4 blocks, right? And that completely makes 100% power consumption, right? So if you're able to optimize power in one block also, like by a 10%, indirectly you are reducing the power consumption by 10% of the system and making it 90%. That itself is also making it power efficient, and that itself is a contribution to the community. Yeah, as well as like the improvements, whenever say it's nothing like you remove one block and you say like, ma'am, we have reduced it to 75%. Yeah, so whenever you design it, it should be making it full advantage of the system level perspective, and it should not make it anything like you are entirely changing the conventional protocol of the transmission and receiving, right? So it should be reforming at the architecture level, but it should be able to take the advantage of the system level as well to design the transceiver as well. Okay, so that itself leads to where we can go further on this. Okay, is it okay till this? Any doubts till this? So after this, we will start discussing more on details of how the transmitter was designed. Okay, I think there are no questions, yeah? Either everyone have understood everything? Okay. Okay, so now comes like before we start discussing about the 15.6 IIRUWB transmitter and receiver, we will discuss one by one about the transmitter and receiver. There are few basic prerequisites which known will be helpful for you to understand the transmitter and receiver in more details. Yeah. So IIRUWB symbol structure, right? So it basically we will be discussing 2 array symbol mapper as well as a 16 array symbol mapper, because these two are the particular symbol mapper which are being mentioned by the standard, right? So we are trying to discuss the transmitter and receiver specific to the standard. Yeah, so let's discuss that, right? So prerequisite, as I mentioned here, like 2 array symbol mapper and 16 array, right? So when I say 2 array, it itself indicates like there will be 2 and 16, right? So 2 array means log 2, so it will basically one symbol, and when we say 16 array, so log 16, so it will be 4. Yeah, so let's discuss this in a little bit more details. Yeah, so when I say I need to transmit a bit 1, okay, and or 0, right? So what is the protocol? So there will be a time window on which you will be transmitting. So let's say like you want to transmit 0, so this has been converted into a code word in a 2 array, right? So 1 0. Similarly, when you want to transmit 1, it will be encoded into a code word 0 1. So now this 1 and 0, this is what you will be transmitting, right? So you can see it up here, right? So 1 0. So the entire symbol duration where you will be transmitting the bit 0 or 1, this is divided into 2 sections, right? And each of equal time, T symbol by 2, T symbol by 2, right? Then again, this is subdivided into like multiple 16 and etc. That itself is called the waveform duration, right? So let's say take an example like square Gaussian pulse, right? Even we can take this, but there can be, just a minute here. So there can be, you can see there is tail also, right? So, but basically the main power consumption or the main pulse is basically in the major lobe and the side lobes, right? So you can see this symbol T symbol is the entire symbol duration. It has been divided into two parts, T symbol by 2 and T symbol by 2. Again, T symbol by 2 is again put up into a number of NW sections, and you can see the time duration of that is TW. That's the waveform duration, right? So here, if you see it up, like for example, 0 you want to transmit. So the code word is 10. That means one pulse will be transmitted at the first section. That means T symbol by 2. And 0 means no pulse will be transmitted on the second section. Then when you are transmitting 1, that means 0 and 1. That means no pulse will be transmitted in the first section and one pulse will be transmitted in the next section, right? So why we are converting this to this position, if you can see in the code word, there is one single one existing in every code word. This indicates even if data symbol is 0 or 1, you need to transmit one pulse. Okay, so what you can see it up here, right? So pulse 0, right? When 0 was transmitted, yeah, am I audible? Yeah, am I audible?
Yes, ma'am.
Yeah, I lost the connection for a few seconds. Yes. Okay, so I was mentioning this, right? So whenever it's being required to be transmitted, we will be transmitting one pulse, even if it's 0 or 1, right? So that it will be clearing it up. There is a pulse, that means the information is been transmitted. We could have used on-off keying as well, right? So where like instead of making a code word, we could say, okay, 0, there is no pulse, right? And like 1, there is a pulse. But while during the transmission, the noise and etc. might put a threshold because we will be using the energy detection at the receiver. So noise might create such energy that might confuse like or might create or might convert the 0 bit to 1 bit. Yeah. I hope this is clear to everyone. Yes. Okay. So next, similarly for this, just a minute. Yeah. Let me clear this. Okay. Okay, so if you see this, right, so this is a 16 array, as I mentioned, 16 arrays, so we will be transmitting 4 symbols at a time, right? So when we say 4 symbols, we are saying like 4 bits, right? So if you can see data symbol binary, it's like 4 bits. So it's like a 16 possible combinations. Here also you can see we are taking, since it's a 4, right? So it will be 4 T symbol. So again, this will be divided into 8 sections, each of T symbol by 2, right? And we have encoded the data symbol to the code word, this one, right? So here if you see, like this is a standard protocol given by the standard. If you see this closely, right, each of the code word is having 4 ones. Might not be arranged in a sequential order, but each one is having 4 ones, right? That indicates that 4 pulse need to be transmitted, right? So this example, what has been given up here, this is related to the blue one, 1001 has been transmitted, right? So the code word for this is 100111001. So you can see 1 pulse is transmitted, 0 no pulse, 0 no pulse, 11001, right? So this is the code word. So based on this, this pulse has been transmitted. So now a question can come up, right? So how to select this particular TW, right? So this position on which this TW pulse will be transmitted, that is also been designed using a random number generator, right? That is also been a part of the baseband, right? Which will tell you randomly which part should be where you need to transmit. But it's for sure like you have to transmit it each of the T symbol by 2 part. Okay, it seems to me, yeah, this is clear to everyone, and this clears like how you are designing the symbol mapper, right? And the most important and most interesting thing, based on this symbol mapper only, you can design the transmitter as well as the receiver, right? So how does it come, right? So you know TW is been ever, so a pulse need to be transmitted here, right? So there where the role of transmitter will come up, right? So transmitter will have a pulse generator, right? And it will allow the pulse generator to generate the pulse only at this window, right? So you can say like it's somewhat sort of gating, right? You are just making it enable only for this time and you are making it off for the other time, right? For example, it's having 16 slots here, right? And you are transmitting it for only one. So that means you are enabling the transmitter or the pulse generator to 1 by 16 into 1000, right? So it's like around like 1 by 8. Okay, it might be like 8% or some part, or 100 by 16 time only you are making it on, right? So this way you are reducing the power to as much as possible. That's what the contribution of 15.6 standard is here as. And then on the transmitter, as I mentioned, so how the receiver logic will also be implemented, right? So what will be the receiver do? Because the receiver don't know which position the pulse has been coming up, right? So what it has to do, it has to do the energy detection of each of this slot T symbol by 2, right? So based once all these 8 energies are collected on the energy detection receiver, then again in the receiver, it will do the back calculation, right? Based on the code word, it will try to find it out what actual the symbol was been transmitted. Yeah, so you can see like transmitter and the receiver are exactly almost the same, right? We can't say exactly same, but if it's in the ascending order of the blocks in the transmitter, receiver will have it in the descending order. Okay, or you can say in the revert direction. The same applies for here as well. Okay, so this comes it up how like we will be discussing how the pulse generator will be designed and how the receiver will be designed. But I think you have understood the concept of how the transmitter and receiver need to be designed. Yeah. So with this, we start discussing the IIUWB transmitter using SRRC signaling pulse, right? So SRRC is a square root raised cosine pulse. Like, so we will be using this pulse for our transmission, right? So we start this 4 points here, right? First, we will discuss like how the IIUWB pulse generation happens, right? And then we will try to discuss how to generate the waveform, right? Using the PWLA approach, right? Piecewise linear approximation, right? Because even if we say like a Gaussian pulse is sort of this, right? But in the real half point, it's not practically feasible to design it in the FPGA. We need to make it approximated, right? Either we suppose this is a Gaussian pulse, we approximated something, okay, we will make it in a sort of triangular waveform, right? Or we will take it in a form of rectangular or something. Yeah, so we will discuss like how the generation of this can be done, right? And then once we will take the different approximation, it can be different approximation, right? Someone is taking the approximation in this way, someone is taking more closely, might be taking some breaks and something sort of this, right? So we will try to discuss like how the different approximations can be taken. And the most important thing is, right, whenever we take the approximation, we should always try to make the approximated pulse as close as possible to the real pulse. Okay. Then once the pulse is been designed or the pulse generator has been designed, right? So we will try to incorporate that in the transmitter and try to make it feasible that can be used for these 2 points. Okay. Okay, and when we say IRUWB time hopping, right? So time hopping PPM means like it won't indicate at which slot it will be transmitted. So it's hoping the time where actually the pulse need to be transmitted. Okay, so before we started working on this, right? So we did a brief literature on IRUWB pulse generation, right? So based on the literature, we came to know it's very difficult to generate the UWB pulse because in the bandwidth is in the gigahertz. So the pulse time width should be in the nanoseconds, right? And to generate the nanosecond pulse in the semiconductor technology, it's not an easy task, right? And that also not in the RF part, we need to design it in the baseband, right? So we came to a conclusion like it's a sort of difficult but not impossible to generate the UWB pulse, right? So some of the existing IR UWB pulse generation approaches which are possible were LC oscillator based also, filter excitation also, right? So filter also, if you pass it to multiple, for example, Gaussian, right? You can design it in some rectangular box. Then you keep on filtering this, right? So you can see after some filters or stages, it will come some sort of Gaussian as well, right? Then digital pulse shaping techniques can also be used. For example, digital pulse shaping means somewhat sort of if you want to generate a rectangular box, like for example, this, I'm just giving an example, right? what you can do, you can generate one block disk from another part, another disk second part, third part, and then you can combine this. And all this will be controlled digitally. Okay. So similarly, age combination also, this was also a technique, and this was done based on the hardware implementation as well in the literature 43 and 44, okay, in the year 2013 and 2007, where they have used a pattern generator. I hope you all are aware about the pattern generator, right? So based on this, right, so we find it out, okay, LC oscillator is not optimal because it will have oscillators and etc. Digital pulse shaping can be used, but it might increase the hardware as well. So there are various pros and cons, right? Please note it down in the VLSI, like whenever you design circuit, always what happens, there will be pros and cons both, right? So if you're trying to make it area efficient, somewhere there will be trade-off on the power, or like on penalty on the delay and etc. Yeah. So what we did, based on the literature, we targeted, like we will design a IRUWP pulse generator. Once the pulse generator has been done and it has been controlled digitally, like where to exactly place the blocks and etc., we can somewhere go ahead and design the transmitter, right? So we try to first target the IRUWP pulse generator because that is the most key component of the transmitter. Okay, so based on designing the PWA, right? So how the concept started, right? As we all know, right? If you charge a capacitor, or if you connect a capacitor by a current source, right? So it will give you a linear line, right? So the same concept what we have used, first of all, instead of going to design a Gaussian pulse, right, we try to generate a triangular wave, right? So if you can see closely, when it's going from increasing slope, that means it's the capacitor is charging, right? And when it's like decreasing slope, that means the capacitor is discharging. So why not use the advantage of the switch, right? So you can see like two switches are connected here, and these are being controlled by the digital signals, where which will be controlling the current source. And if you can see, since the slopes are same, we are putting the same current sources. So as we know, I is equal to C dV by dt, right? So if we control in this way, so we can put it up. Now the most important thing is how to put the VLSI flavor up here, right? So since this capacitor is, and if you remember, like it's an inverter circuit only, if you replace the top switch when it's a charging by a PMOS and the lower switch by an NMOS. So when its input is 0, this PMOS will work and will make it charging, so that there is a path from here to the capacitor. And when it's a 1, this will be working and this will discharge it to there, right? So based on this logic, first of all, we tried to do the proof of concept using the switch concept, right? Then we tried to find it out, okay, this can be used for the triangular. So now if we can see, like since we are wanting both to be the same slope, right? So we were successful on this. So we thought, okay, so this is the same slope. But if you see this graph, suppose we want to generate this. So the slope of the lower two sections is not the same as the top one, right? So this should have the different slope. So how to control the slope? We can't change the capacitor for each one of this, right? So but we can play around with the I, right? So what we can do, we can put multiple different current sources controlled by the different switches, which will be controlled by different digital signals, and which will enable when to connect to one. So if you want like a charging part, number of slopes is suppose 5, so you can put 5 current sources, right? If they are not of the same current values. And similarly discharging, you can put that. So you can see this is a general block diagram where it's like we are seeing n segments. So if you see here segments 1, 2, 3, 4, 5, 6. So we can say 6 segments. And we can put a six current sources here, right? Now based on this, we can see like 1, 2 are only the discharging, and all fours remaining are the sorry, 2 are the discharging and the remaining 4 are the charging, right? So it will have 4 charging current sources here and 2 discharging here. So this is a general block diagram how this can be done. So this was a, if you can see, right, so it was a very basic concept which we tried to apply to design an IRUW. And now the question will be how this time duration will be controlled, right? So that will be based on this input, right? So how much you provide the time period, based on this you can control it, right? For example, this triangular pulse, if you wanted to generate it for 1 nanoseconds, right? So 0 to t should be 1 nanosecond by 2.5 nanoseconds. Yeah, so the time period you can design based on that. So everything is like user control. So you can see, as I mentioned, SSRC pulse, right? So this is the actual pulse. If you can see, we have tried to approximate in different ways, as well as we have to design in such a way that whatever trade-off is, like we should try to make it low power consumption, as well as the most important is the complexity should be reduced. Okay, so we have tried to do it different approximations. If you take the general one, right, so the pulse was like, you can see here it was changing at around zero point 0.9 something. So to make it even clock, we tried to do it with a scale of 1 nanoseconds, right, so that we can use a clock frequency of 1 gigahertz. So this was done for the 4 segment, right? So 1, 2, 3, 4. We have taken this segment entirely from here till here. Okay, third, fourth. This is the first, second, third, fourth. So this was one approximation. Then we took 6 segment again. So 1 segment, 2 segment, and third segment. Why we are mentioning this too? Because we are having different slopes here. 4, 5, 6. Similarly, here what we try to do, we try to make it more breakings, right? You can say like more breakpoints. So what we have done, 1, 2, again 3. You can see a change here. 4, 5, 6, 7, 8. So this was different. So here you can see intentionally we are making like it 8 segment and making it complex, right? But right now to check it out, we can't judge it out based on the visualization which one is best, right? So we try to take different parameters. Based on this we will find it out. The most important is the power spectral density, right? So the real when SRC you take the power spectral of density of that should not be compromised when you take the approximated. Okay, so you can see like we tried to plot the relative error of different things, so we could find it out. The 4 segment was giving the worst relative error, right? And then we tried to do the power spectral density. So you can see like the actual one was a red and this purple one was for the 4 segment. You can say it's going out of the loop, right? So this is not acceptable, even if it might be acceptable in the like number of current sources, right? But this is not this one. Then again we tried with the 6 and the 8 as well, right? As well as we tried to find it out the cross correlation, right? So we can see like this is giving the worst one, so this is almost acceptable in this, right? But here comes the trade-off, right? If you can see like the 4 and 6 and 8 is giving almost like sort of same, and but if you can see the power spectral density, you can see like it's going somewhere out, right? But if you can see the W band spectral mass which was given by the standard, it was somewhere, this was the most important. So everything was being covered it up, so either 6 or 8 is acceptable, but 4 was not acceptable because it went out of that spectral mass. So whenever we design, because we were designing it for the W band application, so we should take the power spectral mass for 2 cases. One is for the actual SRRC pulse as well as the W band spectral. Okay. So 6 and 8, what there was a trade-off, right? Which one we should take? We could have selected 6 and 8, either one of this, right? And we can see like 6 segment and 8 segment is almost giving normalized, and this is here. But if you want the exact, so 8 was the best, right? But when we try to take 8, we saw like it's taking 6 current sources. So when we say 6 current sources, that means it's taking 1, 2, 3 on the top and 3 on the below, right? So it's like you are increasing, then again this switch control. So to make an optimal choice, and as I mentioned, there will be a trade-off, right? So we thought let's take the best choice, even if the power spectral density is matching for that, let's take the 6 segment approximation based on the trade-off between the performance and the implementation complexity. Okay. So based on this, we selected the 6 segment. Now, based on that design, so as we mentioned, like actually, if you now remember, right, so we need to transmit the pulse. So if you can see this closely, right, so this is the TH PPM transmitter which we have designed. So you have seen we have selected the 6 segment PWLA pulse generator, right? So it needs a control of 4 signals, and this is the generator, right? So pulse generator indicates this part. Okay, and this is the external inputs to this. Yeah. So this is the inputs, and there we need a controller. And pulse position, as we mentioned, like where the pulse need to be placed it up. So this you can see, like this all are the controlling part, but the actual part is this one. Along with the controller, this makes it entirely SRRC pulse generator. Okay. And why the use of BB trigger, right? This BB trigger will tell you when exactly you need the pulse to be run. That's what we discussed in this waveform as well. Yeah, when we need to transmit, we will put just this as a rectangular pulse as an input to the SRRC pulse generator, and this will generate the approximated SRRC block. Okay. So here, question can come it up, ma'am, as you mentioned, like they don't require any local oscillator and etc. Right? So, but we are representing this as we have taken the bandwidth of 500 megahertz only. And this was a specification given by the standard that when you are using only 500 megahertz, it's you have to multiply it with a local oscillator. Yeah, else like it can't reach to the particular, because this is the baseband generated here, right? So these are the things from the baseband processor and how etc. things will be collected. So this is a timing diagram how the internal things has been collected. Okay, so you can see these are the blocks, how the internal blocks are being connected here of the controller, and this is the actual most important how the PWLA was done, right? So this part is generating the current sources, right? And this is the controlling part. Okay. Sorry, this is the reference voltage generator part. Okay, and this is what is the thing. Yeah. So this is generating the particular current I1, and this is the controller for that. So you can see how we are combining this and forming it up. And this is the most part. As I mentioned, it will generate when the pulse need to be triggered as an input to the block. And based on the BB triggered and based on the mod counter, when it's off, on, and etc., these four signals will be generated, right? And based on that, this SRRC pulse will do its task based on this part, when to charge, when to discharge, and etc. And you can see here in the time we have put it from 0 to 80 because we will be generating the 8 segments, and which current is responsible to generate which particular segment of this flow. You can see minus I1, that was discharge, right? Now question can come, why direct discharge? Because discharge needs some pre-voltage here, right? So that has been taken up here by this part. Okay, so it will maintain a constant value of like particular might be VDD by 2 from where the discharge will start, and then it will discharge, charge, charge, discharge, charge. Okay. So this was a power spectral density. If you can see, like based on all these blocks and etc., you can see after we have taken the PWLA SRRC pulse, you can see the segment of this is somewhere inside the actual W band spectral mask, as well as it's not violating the FCC spectral mask as well. Yeah, because the this UWB follows the FCC spectral mask as well. Yes. So these are the brief literature on which, and we have targeted to do it in the CMOS 180 nanometer, right? So basically we can say like it's not having a fair comparison because this was designed based on the pulse shaping perspective, and we have designed for the different pulse as well as different pulse duration, different bandwidth. So you can see the power consumption of this is very high due to the digital pulse shaping, as well as it was using the power amplifier as well. So that's also included, right? And for our part, we have used the double balance Gilbert mixer to convert it to a higher frequency. And here you can see the bandwidth is also different. They have used a different modulation schemes and etc. Why we have put this? Because this was only the references which we find it similar to the raised cosine pulse as well as for the respected IIUWB transmitter. Okay? Okay. Is this okay? Till this? Let's take a break for 2 minutes and we continue. Okay, I think there are no questions, so should we continue? Please confirm slides are visible or not.
Yes, madam, visible.
Okay. Okay, so with this we completed the first part, yeah. So it's like we didn't discuss everything in the details, but I think you all have got a rough idea actually how the receiver or transmitter can be designed, right? So now we will discuss a little bit more on the design of the receiver. As I have mentioned, we will be discussing on the non-coherent and the energy detection, and we have discussed as well from the symbol perspective. If you take 16 array, right, so we will have 8 slots where we have to find out the energy of that, right? So but when we design like energy detection based receiver, right, so there might be a few specifications, power and etc, right? So we need to work on the link budget analysis first of all, because there might be internal blocks. So what are the power consumption, then the link loss as well as, right, and what is the sensitivity of the system, right? So it should be like what is the minimum strength that the receiver can detect, right? So all this should be covered it up, and all the specifications are given in the standard as well, right? Then I will give you an idea about the system level architecture of the energy detection, which I have prepared for our work, yeah. Then when we say receiver part, right, definitely it will have an RF front end part as well as a mixed signal demodulator part, right? So when I say RF part, as we have mentioned, we have up converted it using this part. So we have to down convert it as well, right? So how that will be considered into picture, right? So RF front end, but if you see like here, we are using the single to differential LNA and multi-stage. You can see like we have used a square here as well, because this will help us to make the design a bit less complex, as well as since we know we are designing the energy detection, this will do two tasks, right? Squarer. This will first down convert this to the baseband signal, as well as this will do the square of the received signal at the same time with the same circuitry. So this is, you can say, one of the advantage of our design, right? Then we will discuss like after the square we have the baseband signal, right? So now we from the baseband we need to find it out whether it's a 1 or it's 0, right? So when we say like to do, actually what we need to do, we need to do RT. Suppose RT is a receive signal, so square of that and then integrate it at a particular window. As we have seen, the window for us will be T symbol by 2, right? So squaring part is already taken care of by here along with the down conversion. So integration, that part we will do it by the integrated, and we are naming it like windowed integrated because we will integrate at the particular time duration, right? So once after integrated, we will have a single value, right? Might be energy is equal to 10 or 20 something, right? So that we need to convert that analog value to digital value, okay? So energy, if I say like it based on the voltage, if the maximum voltage is 1.8, so energy every value should be less than that, right? Then we will use a single-ended SAR ADC. As I mentioned, like we will be using single-ended because our integrated value is always a positive value, yeah. Then in the digital baseband, once this ADC will happen, we will again back process whatever mapper we have designed, right? From the code we have designed from the data symbol to the code word, right? So that we have to reverse it back from the code word. We have to again make it like analog part. Sorry, we have to put the binary value again, right? From the code word, right? And then that will be forwarded to the MAC. Okay, so as I mentioned, link budget analysis, yeah, this is very much important. And like whenever in the future, if anyone is designing any transceiver design, please go through the standard as well as please look closely into the budget analysis, right? So budget analysis, if you see, like we tried to do for the default mode, generally there are two modes, right? So one is the default mode and one is the high quality of service mode, right? So as we know the basic standard, right? So it has mentioned B means body to body, another is body to gateway, right? So the body to body communication, it will be like on the bodies only the nodes are communicating with the other sensors, and body to gateway, that means like you are sending the data from your body off body to a particular gateway. Okay, so then we have to check it out and you have to find it out what is the link margin, right? And the link margin should always be positive, right? So link margin generally defines the power of the received receiver minus receiver sensitivity. It should be always positive, right? And your power should be always higher than the sensitivity power. Yeah. So these are the few calculations how this can be taken care of, right? And these are the particular path loss equations and etc. need to be converted. And as I mentioned that time, right, for the UWB, this is the particular value, and based on the bandwidth, for example, bandwidth here we have taken 500, right? So calculation, you can see this is the PTX, like the transmitted power which has taken place, right? So based on the transmitted power, the gain of the transmitter and the path loss and the gain of the receiver, this is the power received we can calculate. So you can see how this can be put on the graph as well. So what is the average thermal noise level? So it can't be less than an SNR, and everything need to be covered. Yeah. So I hope this gives you an idea how the link budgeting can be done. At the end, link budget should be positive, and the link budget is calculated by based on the power transmitted or the receiver, right, and by the sensitivity. So this is what my work is, right? So this is the block diagram of the entire energy detection based receiver. As I mentioned, the RF input signal will be received through an antenna, right? So we will use an LNA first here, low noise amplifier, which will, and you can see like we are using a single to differential LNA, so that this generally the antennas which are used are single ended, right? So this will convert into differential, and LNA will try to decrease the noise level. Then we have a multi-stage RF gain as well, because we are converting it to the baseband. And since we have mentioned that the power of the UWB signals is very much minimal, right? It's minus 41.3 dBm per megahertz. So it won't be in the microwatt, right? So to make it into a higher level to be in the milliwatt, so that this, because at the end this is an analog part, right? So we have to, and it's not an RF part, so it's like we are doing it on the baseband, so the input to that should be a little bit higher compared to micro. So once this multi-stage RFA is like trying to increase the gain, and why we are putting multi-stage, we will put various stages of gain based on the requirement, how the strength is, we can enable either some blocks or all the blocks based on the requirement. Okay, and that will help to do the power savings. Then as I mentioned, the squarer, right, it will take the RF signal as an input, so it will make it down convert as well as the square it as well. Okay, so you can see this part is coming up on the RF front end, and this is the mixed signal demodulator. So once the square part has been come, so this has been passed through the windowed integrator, right? So as I mentioned, 0 to TW, or we can make it T symbol by 2 as well. It depends how you are doing it, right? So TW, if you take, you are going more on the power savings as well. Okay, and we will enable it only when it's required. That again leads to power saving. Then the most important thing is like this integrator will be integrating, right? So we are using a particular technique here, right? So how we will be enable which capacitor to store the value. At the end, this integrate will integrate and store it in a capacitor value, right? Because that's also a storage device, right? So how the control of that will be done? So that will be taken up here. So after this, only a single value that will go through the ADC, and we are using 10-bit ADC, right? And we are enabling it only when it's required, right? Based on that, it will go to the digital backend, where this will be converting the code word to the demodulated bits that will go to the MAC layer. Okay, and the digital control of this S1, S2, and everything, this will be done in the through these digital blocks and controlled by a clock and the state. And for your information, this work is already published in the IEEE Circuit Device and Systems. If anyone is interested, he or she can go through this. At the end, I will show you the list of the publications. If anyone is interested, he or she can go through that. So as we mentioned, RF front end, right? So single to differential LNA multi-stage RF amplifier. These are the three blocks in the RF front end, and a mixed signal. It's a baseband integrator. Please note it down. We are mentioning it like baseband integrator or as the baseband windowed integrator, because the input to this is the baseband signal. Then single-ended SAR ADC and the digital backend. So these are the mere calculations, right? As I mentioned, like a multi-stage RF, how the gain calculation will be done, right? So how will we distribute? So maximum receive power can be this, minimum receive power can be this, right? So this is based on the calculation, like minimum distance can be 2 centimeter and maximum distance can be 5 meters. So based on this, we can find it out the power, right? That's what like 2 centimeter to 5 meter is what has been allowed for transmission body to body as well as body to gateway. This is for the body to body, okay, and this is for the body to gateway. And based on the square, we know what is the input power of this. We have done this calculation. That's why we need to increase the gain. So based on this received power maximum and minimum, we can find it out what is the gain required. So we find it out. Gain is like minimum required 23 dB and maximum gain when you take for the consideration of 1, right, when you take the minimum, so it's 69 dB. But please note it down, we need to take into picture of the sensitivity as well. What is the minimum allowed, right? So it came as 71, right? So we should target and we should design the gain to be 71 as a maximum and 23 dB. So now comes it up like how to find it out how many stages are required, right? So as it's mentioned, right, so bandwidth was minimum 500, but when you design the circuit you always take into consideration plus minus 10%, right? So we try to find it out the overall bandwidth for entire, even if you are using one stage amplifier or you are using all the stages, it should be like at least 550, right? So based on this calculation and bandwidth of overall is following this equation, right? So we find it out based on the calculation what should be the gain minimum and maximum and what are the stages, right? And this is what we have checked, like the spectral density and how this should be also taken into the consideration. So when we then based on this calculation, we can find it how to design, right? So here comes the thing how we started. So as we mentioned, RF front end will have 3 blocks, right? So we have used the low noise amplifier and we have designed using the common gain, common source dispatch. So this is the architecture you can see, like LNA, this is the input, right? And we are getting the differential output. Okay, so this has two advantages, common gate and common source. Common gate is the best to make the input impedance matching as well as it amplifies in phase, right? And the common source will also amplify the same but with a phase difference. So the common source will help us to find it out for the opposite phase, or you can say 180, because we need both the phase output, right? And this RLC block will help us to find it out what is the bandwidth it need to allow. And here you can see we have put the EN, LNA, EN, LNA, so that we will enable the LNA only when we need it, right? We are not making it to throughout the operation. Okay, whenever we require, we will enable it and then only we will allow the voltage to work it out and like contribute for the power consumption. Yeah, this somewhat we have taken the reference from these two papers, 2006 and 2004, and we have tried to do it in the 180 nanometer technology. Okay, so how we started doing this, right? So as I mentioned, we try. This is result you can see, like this is for the LNA, right? So bandwidth like 960 megahertz, we got it, right? So based on that, so we can see like this is the 960 and what is the gain it was supporting. Maximum gain is 5.68. Okay, so now as we mentioned, right, the maximum gain is 71 dB and we are getting a gain of 15 dB from already LNA, right? So how much extra gain we needed? LNA will always give 15 dB, right? So we need the gain from the remaining stages to be 56 dB, right? So we have to take all this 960 and as well as each stage gain and all should follow this equation to make the overall bandwidth to be 550 megahertz, right? So now comes the question, which architecture to take for the multi-stage, right? So we try to do it with different possible like PMOS based amplifier, right? So we can design it and like frequency can be taken care by RLC, right? So we try to do it using the PMOS as well as NMOS. Then based on that, then finally we came to know if you use only PMOS or NMOS, so there is always a trade-off. So we try to use the concept of the inverter based design, right? So, and then we try to use this at the amplifier phase, right? And as you all know, right, for the PMOS characteristic, the switching threshold, like for an inverter, right, this is the stage where you can get the maximum gain. So we designed this PMOS configuration in such a way that switching threshold comes around at the VDD by 2 in the bias voltage, and based on that we try to put the input so that we get the maximum gain at the VDD by 2 switching threshold voltage. And if you can see closely this figure as well, you can see the PMOS and NMOS is coming. The combination of the PMOS and NMOS inverter based is giving up here, maximum 2.5. Okay, and as well as the bandwidth values are also given out here. Okay, so based on this calculation and find it out, one stage is giving this, so we will prefer this as well. But before selecting one, we did an analysis on the different types of amplifier, right? PMOS, NMOS, as well as the inverter based. So based on this, just now as we have seen it up here, right? So we are getting the gain of 2.52, but the bandwidth should also be higher because there will be multi-stages. So at the end, the bandwidth will shrink, right? So inverter based result, as we mentioned just now, 2.52 was the gain and the bandwidth was provided 2 gigahertz, right? So as we mentioned, like we need 56 dB gain, right? So 2.5 2.52, what is the gain in the dB? That's around 8, right? So we need 56, right? So 56 dB. So we need 7 stages and each stages will give 8 dB gain, right? So what is the maximum number of gain stages required? Based on this calculation, we found it out 7, and minimum is required based on the gain minimum was 23 dB. Already LNA was contributing 15 and we found. So we try to somewhere make the minimum gain of one stage to be equal to be 23 minus the gain of the LNA. Yeah. So we can see like when we need the minimum strength, if you enable one stage of the multi-stage RF amplifier, it's okay. And when you are based on the distance, you are having the maximum distance, that time you have to make all the stages enabled. Okay. So this was a concept how we find it out. We found it out the cascade of all of that, right? So you can see this is the multi-stage and based on the final output, we put in the square output. Now comes a question again. So if you're only using one, right? So how can you connect it to the square? Either we have to use multiple copies of the squarer or we can use one squarer which will be controlled by the signal, right? So you can see each stage is output is connected to the squarer, and which stage output will be like taken as an input of that will be dependent on the control signal here, right? So this is a complete schematic of the multi-stage and how the control signal will be taken up here. So En RF1, En square 1. So this will be enable which stage to be working, and this will enable which output should be connected to the square. Okay, and the tick and the cross mark indicates close the switch and open the switch. Okay, you can see like it has come up with the 7 stages, each stage contributing 8 dB. So these are the results. You can see like multi-stage when it's like a LNA and one stage. Then you can see here this is like when it's like a LNA and the multi-stage when the number of gain is 1. Okay, so you can see it's contributing to 660. That's acceptable, yeah. This will allow to pass for the 500 megahertz, and you can see it up here. Like even if you started by taking it the 550 megahertz, right? When you have enabled all the stages, then also you can see it's allowing 544. So whenever you design anything for any specification, always try to keep a window. Yeah, but you might see like this result has come directly. No, but we have to do various trials, we have to do recalculations and etc to make it this. Sometimes we try to do and start instead of 540 we start to do it with 530. It landed it up to 490. So that's not acceptable. At least 500 is the fast one, and we should try to keep a window there as well. And you can see how this picture has been come. And one more interesting thing you can see, like as the number of stages have been added up, right? So the frequency shifting and etc. will also take place a little bit. Yeah. So this is the design of the squarer, what we have taken. So this is the values of the differential square plus and square minus. You can see like it's up converted, right? So based on this calculation, the output should be equal to K into VI square. And you can see like this has removed this is the DC part, this is the AC part, right? And this will take the task of the filtering as well. And at the end, you will get only the baseband signal. So this is a simulated response of the squarer. Here you can see that this is allowing the lower frequencies to be passing, and this is the bandwidth. So as you can see, this squarer is also acting as like a low pass filter, and it's allowing the bandwidth of around 244.7 around, like equivalent to that, so that it allows the 500 megahertz or 250 megahertz at the low baseband to allow it. Yeah. So this work, we have taken a reference of a very old literature like 1997. So you can see like various designs to find it. That's why it's called research, right? You need to search it out which one will be optimal and how you can do. So we got the concept from this, and then we tried to do few modifications along with the changes and how to control it that, and try to find it out. You can see we have collected the output here. Okay. So this is the design, like as I mentioned, like windowed integrated. As we mentioned, the square output will be connected as an input. This will be controlling how the different stages and everything will be controlled. So this is the thing how the control will happen. Now, what can happen when this block is integrating, right? That time the another capacitor is resetting again to an initial value, and the third one is in the hold, so that the holded value can go to the next block ADC. So you can say this entire has been divided into three stages: hold stage, reset stage, and the integrate stages. Okay. So that's why three stages will work parallelly in the three capacitors, right? And this will help us to reduce the number of the capacitors, as well as reduce the number of integrators. Else we have to use three integrators, and one integrator is working at one clock, second integrator. So it's like replicating this entirely, right? So instead of doing this, we have replicated like this part into three states, and each one is working at a different part, right? So digital switching control of the capacitance has been taking, and it's like basically we are performing the integration every TW. And what are the three states? We have named them as the reset, integrate, and hold. So please note that this name is not standard specific or not a conventional. This name are given by us so that it's helpful to understand by the name itself. Like reset is trying to reset it to a particular input value, and integrate is when the integration happens, and hold is a point when the integrated value is holding the capacitor, so that at that particular time the ADC, the next block of that, can do the conversion from analog to digital of the square energy value. So this is the block diagram. I won't go into the details of this. Yeah, so this is a single ended SAR ADC what we have taken, and we have tried to design it 10-bit SAR ADC. So what the main contribution of ours in this is, we have tried to design the SAR logic, right, based on the counter based. So what was the advantage of that? So advantage of that, we could reduce the NOR gates and the flip-flop instead of the conventional. Generally, conventional could have used 10 plus to 12 flip-flop, but we are using the seal function of log2 of 10, as well as this many of NOR gates, right? So using NOR gates higher is advantageous than compared to the flip-flops, right? Because flip-flop is again like two latches. Each latch will have for 2 to 4 inverters or NOR gates. That again, it will increase the number of transistors as well. Okay. So this was a switching procedure which taken place. So we are given this example as respect to the 3-bit SAR ADC for better illustration to find it out. How does it work it out? So these are the few comparisons like based on the literature and this work what we have done it up. You can see like the power consumption of ours is less compared to the others, right? And the figure of merit, we can't say this is the best, but it's somewhere higher than these references. But again, we can't have a fair comparison because the objective of each one was different. Someone has designed a differential, some single-handed, some are using op-amp, preamp amplifier, and we are using only a single latch, right? So now the question might come, why we have taken this comparison if we are not saying it a fair comparison? Because we have taken this because all are designed on the same technology, 180 nanometer technology. Okay. So now comes the most important thing and the last block of the IIUWP receiver, digital backend, right? As I mentioned, right? So in the receiver, you will be receiving the pulse and you have done the energy calculation and find it out. Now, how to demodulate it, right? So how does it happen? Let me explain you for the demodulation of two array symbols. So how will you decide, right? So you will have two energy values, right? So based on these two energies, you will do the calculation based on each of the code word, right? So you will find two values, like when you do like for the 0 bit, it was 10, for 1 it was 01. So you will calculate by 10 as well in this equation and 01. This value is what you have received, right? So based on which value is higher, you will find it out, okay, this code word is accepted and this data symbol is applied. So same applies for here. Here you will be doing the energy for all of this, right? And then based on this, whichever energy is maximum, you will say, okay, this code word is the having the maximum energy. So that is what the code word is in, find it out. Once you have the code word, then you can demap using the demapper and find it out which bit is being transmitted. Okay, so what finally we did it out. So based on whatever transmitter and receiver we have done, right? So we tried to do the performance evaluation, even if we say we block and etc. But at the end, for the communication system, we need the BR performance, right? So we have designed the IC of that, and we have done the post layout simulation as well, and we have tried to do it in the channel CM3 and CM4. Right. So what does this channel mean? These channels are the channels specified by the channel model 3 and 4 specifically for the wireless body area network, right? So we have taken that there. If you can see, there is a channel model IEEE standard as well, which we have followed it up and we have tried to do. When it's CM3, it's a line of sight. CM4, if you can see, there are 4 angles. It indicates between the body to gateway. When you are facing same to the gateway, it's 0 degree. But if you rotate 90 degree, it's like a theta is 90 degrees. Similarly, 180 to 70. So based on this, we have done the comparison and we have found it out like it's somewhat acceptable based on this, right? So these are the performance result of only our work we have mentioned, because we can't have a fair comparison of that yet, right? And when we were working on this, okay? So with this, I think we have done an idea of how the receiver will work it out. So rest, I will show you some slides, but I won't explain you that in detail. So even if like for this, we have taken this as a switching technique, right? Later on, we find it out this is not an optimal. So we try to work on the switching techniques to make it further better, right? So we tried to propose one more a DAC switching technique, which is recently published in the Elsevier AU journal as well, right? So what we find it out, there are different methods called split capacitor, merged capacitor, and etc. There is one more given by an authors who, right? So finally, what we find it out, the higher switching energy consumption is done in the first comparison cycle. So if we are somewhere able to make that it to 0, so we are indirectly reducing the switching power to a very lower value and to a very higher extent, right? So this was a proposed one, what we have done it out, right? Then like we did a comparison on that. If you can see, like based on the statistics, right, our power, or you can say the switching energy of our design was 53.0. That was the lowest to others, right? And we have also put the conventional as well, because to have a fair comparison. And if you can see, like we did the optimization to 92.21. Yeah, it's not possible to make the energy directly to 0 and negative, right? Even if like there are a few literatures presently which are trying to claim like energy is coming up negative, right? But as we all know, right, energy can't be negative, right? So mathematically it can be feasible with the proof of mathematical results, but practically it's not feasible. So these are the few statistics, like we try to compare with all the existing whatever we have mentioned, sum of switching energy and etc. And we find it out our one is the optimal. And here we have done it. You can see all these 3 graphs are basically related to the ideal capacitor, but here we try to do it along taking into the picture the non-ideal capacitor. That's where the actual scenario of the VLSI, because there will be introduction of the random noise as well, right? So that will also like put extra addition to the switching energy. So I think I can skip this part, right? So this was another work which we tried to do based on the event driven. So when we say event driven, so in the prior work which we showed in the transmitter, we tried to enable it with respect to the clock, right? But here we are not trying to enable it with the clock, so that we are trying to actually make a generalized one, right? So here what will happen, the output will itself feed back as an input and will tell like how to make the next slope. So you can see, like I can just summarize it up. Clock driven will basically waveform approximated by a sequence of waveforms, and duration of each segment is a multiple of clock. So all segments should be a multiple of clock period, but event driven need not to be that. It's not constrained to basic clock. It will be event driven, and it will basically tell you like on which point. So it has a higher flexibility as well as higher degree of accuracy. But the most important disadvantage of this, the complexity of the controller will be very high. So if you are not targeting to design any application for like low power or somewhere, and you can compromise with the complexity, so then the event driven will be a better option. Yeah. So this is an architecture. You can see like how this output is been again connected as an input, and how this is working as a feedback to do that. So these are the few calculations. So we have tried to do for the same SRRC pulse for the different cases. So as I mentioned, power spectral density, we have taken it up, right? Then relative error we checked. So these are the calculations, like similarly to the prior, we tried to check the number of current sources cross. So we do, you can say we have done a theoretical analysis like how to approximate. And the most interesting thing, and you can say we were successful in this, we were able to make it like independent of clock. And for example, if you are designing some signal, like might be something sort of this as well. Let's take this example. So here the duration is not same, here also not same, here is not same. But if you have used a clock driven, you have to make it all same, right? But if you don't want to make all the duration to be same, then this can be helpful. And I think this will be really helpful for the 5G communication system, where like we need the different waveforms. Yeah. So we did the analysis percentage relative error. So this were the analysis. So then you can see like we did a comparison of the clock driven and the event driven, right? So we could find it out, event driven was giving like more better result compared to the clock driven, even if for the same segment. Okay, similarly for the age segment, right? And as well as adding the advantage without the clock, but at the cost of the higher complexity. But event driven again is higher potential, and it has a better potential to approximate a desired pulse. Okay, so this was the block diagram, as we mentioned, how we did the realization of that using the voltage and etc. So this was a little bit complicated. We are still working on the implementation of that. So this is a block diagram. But here again, the challenge will come it up, like we need the different reference voltages and etc. Yeah. So these were the few examples. We did the analysis for the Gaussian pulse first derivative, and you will be quite like happy to mention this as well, that like we were able to design it for any Gaussian pulse of higher order as so Gaussian first derivative we tried for the third derivative. And the most important thing is, whenever you do approximation, never compromise with the power spectral density. If you can see, like almost here in this case of like for example fifth derivative, right, you can see almost it's matching to the actual, right? But somewhere here this is not, but it's okay, but because everything is lying it up under this. Okay, we try to take n equal to 17. That means we took the best case, like every objective was whether it's making the specifications and etc. Okay. So with this, like we can mention, like I can conclude like our presentation, like we have discussed different methods like based on the clock driven and the event driven PWLA approximation. Then we have discussed the SRRC pulse generator using clock driven, right? And I just gave you an idea how the event driven can also be helped. Then we discussed how the SRRC pulse generator was used for the TH-PPM transmitter, where we have taken the sixth segment, right, based on the trade-off between the complexity and the power spectral density. Then we discussed in concept with the non-coherent energy detection using integrate and digitize. Here I would like to add one thing. Generally in the practical, we use the digitize and integrate, right? So that requires a higher clock frequency. That's not a good option. And we try to take the advantage of that and try to make a non-coherent energy detection by using integrate and digitize, so that it's helpful for the low power application. Then, as I mentioned, like we tried to, as we find it out, switching energy savings can be done in the first comparison cycle. So we tried to give some suggestions and try to introduce a new DAC switching technique. And lastly, as I mentioned, like we have tried to mention about the event-driven PWLA, and based on the theoretical analysis and the simulations, we find it out. It seems promising to make the practical applicability of the IIUWP transceivers, and it's nothing like only IIUWP, it can be applied for the narrowband or anything as well, wherever you need to design the pulses. As well as this PWLA pulse generator you can use in the coherent receiver as well, right, where you need to generate the template at the receiver end as well. Okay, So the future scope of the work, if you can say, like, if you see, like, we have designed for this. So these are the different data rates provided by the IEEE 802.15 standard. So our design can be used for all these data rates. Just we need to change the clock duration and the input clock frequency. That's what you can say. We have although targeted it for the default mode, right? But this can be applied for any higher. That's what like was the contribution mode. Even if to come up with the final circuit, it took a lot of time, but we are happy at the end. We have been able to design a circuit which can be generalized. Yeah. So future scope, as I mentioned, the event-driven waveform generator, they can be also used like for the carrier-less as well as a carrier-based as well, right? So in the future work, we can also target to design a dual standard effective for 15.6204. And if you have seen, WPAN has also released like in 2015 a new WPAN standard. So exploration, and if you can see, if you go through the standard, you can see both of them are having somewhat 10 to 20% similar like specifications. So then the most important, as we discussed, IRUWB, even if we are focused on that specific to 15.6, right? But how to apply it for the IoT based healthcare, taking into the consideration the minimum size and the low power as well, that can be explored. Yeah, so this comes like the publications, like what we have covered it up till date. So in 2020, we have gone through this two publication based on this was for the single-ended SAR ADC, as I mentioned. And the next one on the transmitter, right? The entire whatever I have described. And based on the receiver, we had published a paper in IIT circuit divisor system. And these are the first, this was the first work which we covered it up on the SRC. And these are a few demodulation techniques which we have tried to engage in that. Yeah. So with this, I end the presentation. Thanks a lot for your patience. Yeah. So I'm open for the questions. Yeah, someone has posted a question. In what technology the RF front end was and what noise figure was achieved? Yeah, so here I would mention, like, I have tried to implement the entire system in 180 nanometer technology, UMC. Yeah, noise figure achieved. Ma'am, I'm not able, ma'am, or sorry, yeah, Pranav Manoj, I am not able to recall that exact value, but it was somewhere meeting the required specifications.
Madam, your system was fabricated?
No, at the end we could not go to the final. We have completed till the GDS, but we could not go for the fabrication due to few constraints.
Okay.
Yeah, any more questions?
Regarding the whole system design, is there any optimization technique for whole system design?
I think no, because each blocks has different specs and different constraints as well. So we have to look into that and put it up on that way. Basically, you can say like a block level optimization is possible, but when you use a system level optimization, you can play around with the specs as well in that perspective, because there are a lot of trade-offs and etc. So you can say overall system, RF and the baseband, as well as like you can say the demodulation part, all will have different constraints based on the frequencies as well.
That means we will have to adjust all the trade-offs manually at the system level.
That's what the VLSI part comes it up. Yeah, we have to look into the trade-off as well as we can't deny with any of the trade-off.
Okay, madam.
Yeah, any more questions? Okay, I think if there are no more questions, so I would like to thank you all the participants for your patience and for bearing it up with me for the last 2 hours. I was very glad to answer few of the questions. If later on anyone is having any doubts or any queries, you can just approach me over mail as well, right? So all the details, I am a faculty at IIIT Gauhati. You can get the email address there, and I'm open for the research domain. You all can go through the links as well, right? And as well as I'm working in the last you can say 1 year or 1.5 years on the quantum computing, and that's where the revolutionaries happen. So anyone is interested can join our team as well. Thanks a lot. So over to Mr. Kolita.
Okay, thank you, madam, for your informative talk.